Welcome to Lecture 20, the second of our two lectures on fluid behavior. This time we're looking at fluid dynamics, the behavior of moving fluids. And our simple picture of fluids is represented by density and pressure. It gets more complicated because when they're moving, we've also got to talk about the flow velocity. Just like density and pressure can be functions of position, so can the fluid velocity. Furthermore, with fluid dynamics, all three of these quantities might vary with time, even at a given position. So we've got quite a bit more complication. But we're going to simplify that because we're going to talk about one special case in which neither density nor pressure nor velocity vary with time at a fixed position, although they may vary from position to position. Let me show you what I mean by that. Here are videos of a couple of rivers. The river at the upper left is exhibiting essentially steady flow. The river is flowing. The water isn't the same water at a given point. As Heraclitus famously said, you can't dip your foot into the same river twice. But at every given point, we can identify a definite flow velocity. In the unsteady flow, turbulent flow, you'll notice that the flow is changing with time. Water bursts up out of the surface and then settles down a little bit. The flow is continually changing. With the flow at the upper left, I can add arrows to that flow, indicating the velocity at each point. And again, even though the water is moving, those arrows stay the same length and they have the same direction. They represent the velocity of that flowing fluid. Another example of an unsteady fluid flow would be the flow of blood through your circulatory system. As your heart beats, the blood gets higher pressure and moves faster, and then it slows down again. So the beating heart is producing an unsteady flow. And in the rest of this lecture, we're going to deal exclusively with steady flows. The mathematical treatment of unsteady flows, of the phenomenon called turbulence, is a very difficult, almost intractable mathematical problem, and it actually remains an area of contemporary study in fluid dynamics. So we're not going to go there. We're going to look at steady flows, but we have a lot to say about steady flows. How do we represent moving fluids? Well, one way we do it, or could do it, is by simply drawing a flow vector at every point in the fluid, or at representative points. So something like this. Here's a sort of symbolic picture of a river, for example, flowing through a region where the river gets a little bit narrower for a while. And what I've done here is to indicate by arrows the direction and magnitude of the steady flow of that river. So the length of an arrow is the magnitude of the flow. These are vectors, velocity vectors. The direction is the local direction of the flow. You can see the flow coming down, going straight and getting a little faster in that narrower portion, and then expanding outward again at the end. That's one way to do it. Another way to represent the flow is to draw what are called streamlines. These are continuous lines that are everywhere in the flow direction. And the remarkable thing about doing that is you get a picture that not only shows you the direction, but it also shows you the magnitude of the flow velocity. And you can see that the lines are closer together in that constricted region of the river where it's narrower, and where in the vector picture the vectors were longer, the flow was greater. Here the flow lines or streamlines are closer together, and that is an indication of the strength of that flow, the speed of that flow. By the way, we'll use a similar kind of continuous lines later on when we talk about electromagnetism, and we will represent electric and magnetic fields with the same kind of idea. And this is, in a sense, the velocity field of this flowing river. We can visualize the velocity field in some cases by adding some kind of material, maybe dyes or particles, to a stream of fluid that show you the actual fluid lines. And here is an example where a car is undergoing aerodynamic testing in a wind tunnel, and we've introduced particles of smoke into the wind at specific points, and those particles are tracing out the streamlines of that fluid flow so we can directly understand what's going on in that particular flow. Okay, so that's a look at how we're going to talk about dynamic fluids, fluids that are moving. What we want to get to is two conservation laws that describe what's going on in flowing fluids. And these are big, important conservation laws, not just for fluids, but for all of physics. But we want to express them in particular forms that apply to flowing fluids. They are conservation of mass. Matter is conserved. It doesn't appear or disappear. Einstein out of the picture for now. We'll talk more about that later. But in normal everyday operation, mass is a conserved quantity. and so is energy. And we've seen the importance of energy conservation. So we want to spend the rest of this lecture looking at conservation of mass and conservation of energy in flowing fluids. We want to understand how to express those in equation form and then how to handle those to explore the behavior of flowing fluids. So let's begin with a look at the conservation of mass, which is the easier of these two to deal with. How do we conserve mass in a fluid? Well, first of all, I want to define something called a stream tube or a flow tube. A flow tube is a narrow region in a flow. So here I have a picture of a flow with some streamlines. And the streamlines show, for example, that the fluid is flowing to the right and that it was flowing with lower velocity at the left than it is at the right because the streamlines have gotten closer together. And I want to focus on a very narrow tube bounded by adjacent or nearby streamlines. Now, of course, there are streamlines everywhere. I could draw infinitely many streamlines. So this is kind of a loose idea, and I'm sort of taking the limit as I get towards streamlines that are very close together. I'm making that tube small enough that fluid properties like pressure and velocity and density don't vary significantly across the area bounded by that stream tube or that flow tube. So that is how I'm defining this small flow tube. And nevertheless, the tube may reflect changes in fluid properties as you move along the tube. The tube is narrow enough, there's not much change in fluid properties across the areas. They may be different, though, at this end than at this end. So that's my concept of a flow tube. Two nearby streamlines define the flow tube. It's as if it were a pipe of that shape. It isn't a pipe. It's just an arbitrary mathematical surface. But because fluid flows along the streamlines, no fluid flows perpendicular to them, so you can think of it as if it were a pipe. If you put a perfectly frictionless pipe there, in fact, the fluid would behave pretty much the same way. So that's my idea of a stream tube, of a flow tube. In steady flow, fluid comes into this tube at the same rate that it goes out. So here I've shown a little chunk of fluid just about to enter my flow tube. And here I show a chunk of fluid just about to go out of the flow tube. And because the tube is narrower, this chunk of fluid occupies a longer space because it's got a smaller area. So I'm going to assume that these two flow elements, these two elements of fluid, have the same mass. How can I assume that? Well, I'm just going to make it be that way. I'm going to measure the mass of this one. I'm going to find out how much of the fluid I need to get the mass of that one. So these two have the same mass. And because the fluid is flowing in steady flow, however much fluid comes into the flow tube in 1 second, that much must exit at the other end. If that weren't true, we wouldn't have steady flow because we'd either have fluid accumulating in the tube or fluid being depleted from the tube. So in steady flow, these two fluid elements with the same mass must take the same time to enter and leave the flow. Now, the mass of a fluid element with density rho, area A, and length L is the density times the volume, rho times A times L. And rho and A and L may all be different at the two ends of the flow tube. The fluid element is moving at speed v. Here it's v1, here it's v2. The speed may be different at two ends of the flow tube. And so the length of the flow tube, or the length of the fluid element about to enter the flow tube or about to leave the flow tube is v times that time delta t in which this fluid element is going to enter and in which this fluid element is going to leave. So far, I'm writing these quantities without any subscripts because they apply to either end of the flow tube. So I can find the fluid element mass. It's rho times the area times the length. That's rho, the density, times the area times the length, which was v delta t. And that expression, again, applies at both ends of the flow tube. And the masses are the same, even though the density, the area, and the speed may vary. The time is the same because we've said it takes the same amount of time for that mass, m, to enter as for that mass, m, to leave. So here we have it. The fluid element's mass is rho A times the fluid velocity v times the time delta t it takes it to enter or leave the flow tube. Now in steady flow, again, the masses entering and leaving the flow tube in time delta t are the same. So if I put subscripts 1 on the density, the area, and the velocity coming into the flow tube, and 2 on the density, velocity, and area coming out of the flow tube, then those two quantities are equal. Again, the delta t is the same because this mass, this fluid element is entering the flow tube in the same time that this one is leaving. So I can write that rho 1, A1, V1, just dividing, canceling the delta t, is equal to rho 2, A2, V2. Equivalently, the quantity rho AV ends up being a constant along a flow tube. So that's a statement. That English language statement, are equivalently expressed entirely in mathematics, where 1 and 2 designate any 2 points along that flow tube. That is a statement that that mass is conserved in a steady flow. That's how mass is conserved in a steady flow. Let's take a further look at that equation we just developed. So we'll do an anatomy of the equation. That equation is called the continuity equation. There are a number of continuity equations in physics, and what they express is the conservation of some conserved quantity. For example, there's a continuity equation in electromagnetism that expresses the conservation of electric charge. Here we have a continuity equation that expresses the conservation of mass, in this case the conservation of mass in a flowing fluid. There's our equation. Rho times area times volume is a constant along the flow tube. You identify a flow tube, you pick the values of rho and A and V at one point, you measure them at some other point, and in steady flow, they must be the same. Because no fluid is leaking out of that tube from the sides, so whatever fluid comes in has to go back out. That quantity has to be a conserved quantity. Rho is, again, the fluid density, A is the cross-sectional area of the flow tube, and V is the flow speed. And that quantity, rho AV, is constant along a flow tube. It's a constant for a given flow tube. It may vary from place to place as you move sideways in the fluid perpendicular to the flow. You may find these quantities vary. You may find they don't. It depends. But they could. This is constant, though, along a flow tube, along a given flow tube. And this quantity, rho AV, if you work out the units of it, mass per unit volume, area, mass per cubic meter, meters squared, meters per second, work that all out, and you find the units of that are kilograms per second. So that number that's constant is the mass flow rate. It's the number of kilograms per second flowing through the flow tube. At any point in the flow tube, you sit there, and that many kilograms per second go by you. And that number doesn't change as you move along the flow tube. That's the statement that the mass is conserved. Mass isn't appearing or disappearing. Conservation of mass. Now, in liquids, as we've seen in the previous lecture, for liquids, the density is a constant because the molecules in liquid are close together. It's hard to compress it. That happens to be also approximately true for gases when they're flowing at speeds that are much less than the sound speed. It's that property that makes gases behave sort of like liquids at speeds well below the sound speed. And it's also that fact that makes the whole business of supersonic aircraft flight a very different physical process than subsonic flight, because the gases behave actually very differently at supersonic speeds than at subsonic speeds. So for liquids, rho is a constant, and it's also approximately true for gases at subsonic speeds. And then we can just cancel the rho, because it's also a constant, and we have another constant, just A times V along a flow tube, and if you work out the units of that, that's cubic meters per second, so that's the volume flow rate. So let's do an example where we use this equation whose anatomy we now understand. Here's a beautiful river in upstate New York, the Ausable River. Lovely river, flows through the mountains, the Adirondack Mountains, and eventually down into Lake Champlain, northern part of Lake Champlain. And it's a beautiful canoe stream. Early in the summer, it's typically 40 meters wide, about 2 meters deep. Of course, rivers vary, and it's flowing at about 4 meters per second. Just before it enters Lake Champlain, it goes through this gorge called the Ausable Chasm, and at the narrowest, it's less than 4 meters wide. Remember, it was 40 meters wide in the normal flow. It's flowing at speed of about 6 meters per second, about 50% faster than it was before. And the question is, what's the depth in this chasm? Well, we can work that out using the continuity equation. It's a liquid, so A times V is a constant. We don't need to worry about the density rho. A is the width times the depth. I'm assuming it's got kind of a rectangular cross-section. In the normal river, it's 40 meters wide, 2 meters deep. It's flowing at 4 meters per second. So AV is 320 cubic meters per second. So again, we are looking at the Ausable Chasm, 3.7 meters wide, 6 meters per second flow speed. We found the volume flow rate. It's 320 cubic meters per second. That's the flow rate anywhere by conservation of mass. So in the chasm, the thing we don't know is the depth, d. So we have the width, 3.7 meters, the unknown depth, d, the 6 meters per second. They have to multiply together to give 320 cubic meters per second. We solve for the unknown depth d, and it's 14 meters or 47 feet. Wow, that's deep. So there is an example of the use of the continuity equation to tell us something about a flowing fluid. Well, that was conservation of mass. Now let's move on and talk about conservation of energy. And when I talk about conservation of energy, at first, I'm going to say, let's assume there's no friction or anything sapping energy from the fluid. Let's suppose we haven't put any pumps in the fluid to add energy or put in turbines to extract energy, and we want to develop an equation that expresses conservation of energy in a flowing fluid. So that equation is called Bernoullis Equation, and it's the equation that expresses conservation of energy, and I'm going to restrict myself here to incompressible fluids, meaning fluids for which the density is constant. So here's the question. I'm going to start again with a flow tube. I haven't bothered to draw the flow lines, the streamlines, but here's a flow tube, and this flow tube rises in height an amount delta y from one end to the other. There's a pressure P1 at the one end and an area A1, and it's fluids coming in with velocity V1, and a hunk of fluid delta X1 is coming in. And I'm going to talk this time about the same fluid element as it comes in and as it exits. And I want to know how much work is done on that fluid element as it moves from the coming into the flow tube, coming out of the flow tube. We're going to apply the work energy theorem that we developed in lecture 11 that says the change in kinetic energy is equal to the net work done on an object. So here we're applying good old Newtonian physics to this more complicated case of a fluid. Work is force times distance. Well, coming in, there's a pressure force, pressure 1, the pressure at the inlet, times the area, and the fluid moves a distance delta x1, so force times distance is P1 A1 delta x1. Going out, there's a pressure P2 from the external fluid. It's pushing back, so instead of doing work on the fluid, positive work, it's doing negative work. So going out, we have minus P2 A2 delta x2. The work done by gravity, well, as the fluid rises, gravity is pushing downward. So we're working against gravity. We would have to do positive work. Gravity does negative work, and it's minus mg times the height, which is, in this case, delta y, or y2 minus y1. So there's the work done by gravity as we go through the flow tube. So we're still asking this question. How much work is done? We've got three contributions. Incoming work from pressure, outgoing work from pressure, and the work done by gravity. So the net work is the sum of those three, two of which happen to have negative signs. There's the net work done on that fluid element as it goes through the tube. The kinetic energy change is the kinetic energy at the outlet end, a half mv squared, v2 in this case, the velocity it has at the outlet, minus the velocity, the kinetic energy at the inlet, 1/2 mv1 squared. And what work energy theorem tells us is that the net work done will be equal to the kinetic energy change. So we're going to equate those two, and I'm going to divide by the volume A times delta X of the fluid. In each case, if it's an incompressible fluid, its volume hasn't changed. Its shape may have changed, but its volume hasn't changed. And so there I get that expression when I divide by the volume, and dividing by the volume turns the mass into mass per unit volume, or density, which is why the density appears there. So there's my almost final expression. I just do a little algebraic rearrangement, put all the terms with the 1s on one side, all the terms with the 2s on the other side, and I have this quantity P1 plus a half rho V1 squared, plus rho gy1 is equal to the same thing with the 2's at the other end. Equivalently, that quantity, pressure plus a half rho v squared plus rho gy, is constant along that flow tube. Okay, let's take a closer look at that equation and see exactly what it says. It's called Bernoullis Equation. As we saw, it expresses conservation of fluid, of energy in a flowing fluid. It's restricted to incompressible fluids, and let's look at the individual terms. Clearly, the second term is like kinetic energy but divided by volume, so it's an energy density. The third term is like potential energy but divided by volume because it's got rho instead of mass. It's an energy density, and pressure is also a measure of the density of a kind of internal energy associated with molecular motions in the fluid. We'll talk more about that when we get into thermodynamics. That quantity is constant along a flow tube. The pressure, an internal energy density, the kinetic energy density plus the gravitational potential energy density, those add up to a constant, but individually they can change. You can change energy back and forth among different forms in this flowing fluid. And that's what we want to look at in a little bit more detail. That constant, again, is a constant for a given flow tube. It may vary from flow tube to flow tube, but as you move along one flow tube, that quantity stays the same. Frequently, we deal with cases where there's no height change. A pipe running along horizontally, for example, a river flowing horizontally. When there's no height change, then we can drop the rho gy because that's constant. That's the same on both sides of the equation. And we simply have that the pressure, that internal energy density, plus the kinetic energy density adds up to a constant. And that property is called, that's called the Bernoullis effect, the fact that pressure and something involving velocity add up to a constant, because it says that in places where pressure is high in a flowing fluid, other places on the same stream tube where pressure is lower, the velocity will have to be higher. Now, this principle often gets misused. This is called Bernoullis principle, and it's the Bernoullis effect is this effect whereby high pressure goes with low velocity and vice versa. Be careful. It's only true as you move along a flow tube. It's not true that if the pressure is high here, then the velocity will be low over here. It's only true along a flow tube. P plus a half rho v squared equals constant. A couple of examples of that, of this high pressure with low flow speed and vice versa. In an airplane wing, the flow over an airplane wing, the wing is designed so the flow speed over the upper part of the wing is higher than over the lower part of the wing, and that, in turn, by Bernoullis effect, causes lower pressure above, higher pressure below, and that's one way of looking at what supports an airplane. By the way, I think it's easier to think of an airplane in terms of Newton's third law. What that flow is doing, you'll notice the outgoing flow is pointing a little bit downward, and so the wing has deflected air downward. It's exerted a downward force on the air, and the air has therefore exerted an upward force on the wing. It's not a contradiction with Bernoullis effect, because the whole Bernoullis equation came out of Newtonian physics, but in this case, a simpler version based on Newton's third law, I think, is more effective. Look at how a curved ball behaves. A ball that is moving through the air without curvature, without spinning, has a symmetric flow around it, and the pressure is the same on either side. But when you set the ball spinning, friction of the fluid with the ball entrains some of the air with the spinning ball, and it causes a higher flow on one side of the ball, flow speed on one side of the ball. That causes a lower pressure. This picture, we're looking down on above from, say, a pitched baseball, and that causes a force that deflects the ball in the horizontal direction, assuming it's spinning about a vertical axis. So that's the Bernoullis effect, the presence of high pressure with low speed and vice versa. Let me give you a few examples and applications of the Bernoullis effect. So over here, I have a rather loud blower, and I want to be very clear that it is blowing air out, away. You can see it doing that clearly. So we know that air is being blown outward. Here's another obvious case of that air being blown outward. That air column is supporting that ping pong ball. Not surprising. It's in a symmetric situation, so the air speeds on both sides of the ping pong ball are the same. But now what happens if I do this? The ball ought to fall. The air column is not pushing it straight up. It's not counterbalancing gravity all by itself, it seems. And yet the ball is happily supported there. What's going on? Well, the situation is no longer symmetric, and the airflow is, in fact, faster over the upper half of the ball than over the lower half, and that results in a lower pressure, and the higher pressure below, then, is effectively supporting that ball. And I can tip it quite a ways down before that effect ceases to be useful. Here's another example. I'm going to attach this funnel to the hose, and I'm going to take this balloon, and again, that air is blowing out of that funnel, away from the balloon. You can see the balloon kind of blowing away. But now I'm going to put the balloon in the funnel, and at some point, even though the air is flowing out, the balloon is sucked into the funnel and held there by some kind of force. I got to pull it to get it out. Why did that happen? Because when the air was flowing out of that hose, the presence of the balloon created a very narrow space between the balloon and the funnel, and that caused the air to flow very rapidly, and by Bernoullis' equation, that caused the pressure to be lower because of the rapid flow. As the flow expanded, when it got outside the funnel, the flow speed dropped, the pressure went up, and so the higher pressure down below and the lower pressure up above forced the balloon to stay in the funnel. So those are some examples of Bernoullis' effect. And the Bernoullis effect can be quite counterintuitive and quite fascinating. Okay, so let's look at some more serious applications of Bernoullis' principle, and we'll actually work an example of one of them, and I'll let you do an example of the other one as a challenge. So here are some pictures of applications. One is the way we measure speed in aircraft. We measure speed with a device that senses the airflow one way by stopping the air and causing the velocity to be zero, and another way that samples it, letting the air go by at its normal speed. And by comparing the pressures at those 2 points and applying Bernoullis' principle, we're able to calculate the actual airflow speed. That's how aircraft use speedometers, if you will. Another example shown at the bottom is the dangerous situation of arterial stenosis, in which plaque builds up in an artery, restricts the flow of blood in the artery. And you might think that would lead to higher pressure, but for all other conditions being equal, what it leads to is higher flow speed by the continuity equation. Fluid has to move faster to get by that limited area, and that results in lower pressure. And in extreme cases, you can actually collapse the artery because the pressure in it gets so low that external pressure collapses it. And I'll let you think about that in a challenge problem I'll give you shortly. Let's look at this aircraft speedometer in a little bit more detail. This thing is called a pitot tube. And in my example, I'm assuming a plane is flying at 33,000 feet. That's about 10 kilometers altitude, where air has a density of 0.41 kilograms per cubic meter. The pressure difference in this speedometer between point A and point B. Point A is where the air is flowing right by with its normal speed v. Point B, the air has come right into the tube and is forced to stop. Let's assume that difference, measured by that pressure indicator, is 15 kilopascal. What's the plane's airspeed? Well, the Bernoullis principle applies. The sum of the pressure and the kinetic energy density is the same at both points. VA is the unknown airspeed. VB is 0 because the air has been stopped. So PA plus 1/2 rho V unknown, the airspeed squared, is PB. There's no second term on the right-hand side because the air has been stopped at B. V is 0. So there we are, or put it a different way, 1/2 rho VA squared is PB minus PA. Pull the PA to the other side of the equation. That's the delta P we're measuring. So let's solve for V squared. There's V squared. V is the square root of that. And if we do the numbers, this airplane is moving at 600 miles an hour, a typical speed for a jet airplane. So there's a realistic example and a practical application where we use Bernoullis' equation to learn something we couldn't learn by running a wheel along the ground like in a car speedometer, so we have to do it some other way, and we use Bernoullis' equation. So let's move on and wrap up with just a few other points about Bernoullis' equation and fluid energy. Sometimes fluid energy is not conserved. Let me give you a couple examples. Fluid does have a kind of friction, and that friction is called viscosity, and it's particularly important when the fluid is flowing near a stationary material boundary, like the walls of a pipe. So if you have a pipe, instead of the flow being uniform across the pipe, it's 0 precisely at the edges where the fluid is literally attached to the boundary, and then it increases toward the middle of the pipe. And how important that effect is depends on the width of the tube in relation to properties of the flowing fluid. So for water in pipes an inch or 2 in diameter, it's not a big deal. Molasses or honey flowing through the same pipe, it would be a big deal because those are very viscous fluids. So we have high speed in the middle, low speed, 0 speed right at the walls. Another example is if we put turbo machinery, that is pumps or turbines, into the flow. Pumps add energy to the flow, so they put another term in Bernoullis' equation. Turbines extract energy, and the kind of turbines we think most about these days are wind turbines. That's one of the fastest growing new forms of energy. There's a picture of a wind turbine. And if you think about the energy density in a fluid, it is 1/2 rho V squared, but that energy is moving along with fluid speed V, and that makes the energy flow in the fluid proportional to V squared times V, or V cubed. And since that means if you simply double the wind speed, you will cube that effect, that is 2 cubed, or 8 times the amount of energy being carried in that wind. And that tells you one reason why wind turbines need to be high, because that viscosity slows down the air at the ground. You have to go up quite a ways, tens of meters, before you get rid of that so-called boundary layer effect from the ground. And at high heights, you get winds that are much stronger, and a small change in wind speed because of that V cubed makes a big change in the amount of energy you can extract from the wind. Okay, let's wrap up. We've visualized fluid flow with streamlines. We have found the continuity equation to describe the conservation of mass in a fluid flow, and rho VA became the constant quantity. We looked at Bernoullis' equation expressing the conservation of energy. We had this more complicated sum of 3 terms, pressure, kinetic energy density, and potential energy density being constant in a flow tube. And that led us to Bernoullis' principle, high velocity, low pressure, and vice versa. Well, let me end with a quick challenge to you. Find a formula in that picture of the stenosis for the pressure at the stenosis in the clogged artery. In terms of the blood density rho, the normal blood pressure P sub naught, pub sub 0, the normal blood flow speed V sub 0, the normal artery area A sub 0, as shown in the picture, and the area A at the constriction. And we're going to assume the pressure doesn't vary with time, which is not true, of course, for blood because the heart is pumping all the time and the pressure is going up and down. But we'll just assume that for a simple example. And I'm not going to work out the solution in all its detail, but I'm going to give you a hint. You will need to combine both the continuity equation and Bernoullis equation, those two conservation statements we derived in this lecture. And take your pencil and paper out and go to work. And here is the answer. Answer to that challenge is this complicated expression, but it involves the difference of the squares of the two areas. If the two areas are the same, there is no pressure difference. If the areas are different, there is a pressure difference. And if the second area is smaller, the pressure actually drops.